Before we start learning how to properly predict the height of tide and the speed of a current, I want to go down into a little bit of detail on kind of the structure of the mathematical representations of how tides work. You've probably seen tides represented with a sine wave before, and it's pretty intuitive why. They obviously come in a cycle. Two high tides a day, two low tides a day, constantly going back and forth. But even if you've already seen it, this is really the best way to represent that on a graph so that you could quickly understand what's going on. If this direction here is time, and this is just the height either above or below the vertical datum, which I think I went into when I was going over the charts, but I can if I haven't. This just shows the water rising above the normal water line over time, then slowly petering out, dropping back down, and so on. So you could clearly see that this point right here is a high tide, and this point right here is a low tide. And it continues, obviously, into the future. Now, what's important to remember about this is that it is not, well, if you know anything about calculus, the slope of the line here, as it changes, will almost be kind of offset in its magnitude from what this looks like here. What I mean by that is that the point on this graph with the highest in magnitude slope, the 2 points are right here and right here, and I suppose right here as well, but that's barely on the page, because that is where obviously things go from nearly horizontal. At the high tide, it's perfectly horizontal, the slope of the curve, to leaning back downwards until it's nearly perfectly vertical right at this point before it moves on. Now, this graph representing the height of the tide, its slope, which is, change in height over time, you can think of that as the speed of how fast the water is moving to either fill in the land or pull away from the land, which is, essentially the same, or it is the same as the tidal current. So these 2 points here are the points of time with maximum current, and it's right when you're transitioning from high tide into low tide, or from low tide into high tide. So you could imagine the water is coming in really fast here into the land, slowing down a little bit, a little more, right until here when it nearly stops, or it does stop for a short period of time, and then slowly starts to retract from the land a little faster, until at this point it's the fastest it's going to be moving, and then continues the same process of slowing down, stopping at low tide, and speeding back up. With that in mind, you can see that the height of the tide and the speed of the current are inextricably linked. They're one and the same, and technically the speed of the current is just the derivative of this graph, and therefore can be represented, I'll do this in a dotted line, as such, where the height of tide is 0, the speed of the current is maximum, either positive or negative, and where the height of tide is maximum, the speed is 0. Because of this relationship here, and because the slope of a sine wave doesn't necessarily change, it can principally follow along. As long as you know the amplitude of the wave and its frequency, you can always predict how it's going to curve. What that means is it's actually very easy to predict into the future what tides and currents are going to look like, because you can just replicate this graph out as long as you can predict how high it's going to be and how often the tides change. And luckily, the way the speed and cyclical nature of the tides are pretty predictable in certain areas, or each area of the world, it's relatively predictable for that area. So as a result, I believe it's NOAA, is able to publish the tide tables a year in advance consistently without having an issue of regularity or of accuracy. That reminds me, I had a friend who went through all of TNAV and then somehow still had the belief after TNAV that the tide tables were a historical document, as in they were referencing the previous year and would just tell you what the tide was like in the past and that it didn't have any predictive capabilities. It blew my mind because I think he claimed that his teacher specifically said that to him. So I don't want you to get that impression that this is all about just knowing what it was like in the past. This is a predictive model. And to predict it, there are 3 or 4 things you need. Like I said, first you need the amplitude of the wave. Now, that's the mathematical term for it. What we'll describe it as is the range of the tide. And instead of going from high to 0, we measure the range of the tide as the total difference in feet between high tide and low tide. So this can be the range. Don't get confused when you look into the tide tables that high tide can sometimes be something like 7 feet and low tide will be like 2 feet or like 0.3 feet. I think that throws people off that low tide is always so much lower. That's because the vertical datum is defined off of mean low tide anyway. So it's not, this line should almost be closer to down here. So it's not likely for you to get that low below what the datum is, whereas you can get much higher. And that's why it always looks like that. That's why low tide always seems smaller, but they're both equally large. Now, or they can be. Next, what you would need is the duration of the tide. So you could think of this as like the wavelength of the curve, but it's not a full wavelength. Instead of from high to high, this time we're just measuring from high tide to low tide in time. So how much distance was traveled to go from high to low or low to high, it doesn't matter, and how much time it took to get between the two. With these two factors, you can pretty regularly take a normal sine wave, adjust it to fit these two, and you can predict where at a certain point in time what the height of the tide will be and what the speed of the current will be all throughout that curve.